Greetings, Earthlings. Today we're looking at that Geoboard problem that I presented in class at the end of the day. Here's a video of the solution. So, I already drew out the square here. You might want to take a second to copy it down. Here, I'll even highlight the lines just a little bit. Okay, now that you've copied it down, we see we have the square constructed with an outer square around it too. Well, we don't know just exactly what it is the inner square is because we can't measure these directly, but we can measure this big outer square, right? These are straight lines on the dots themselves. So we'll count. This seems to be 1, 2, 3, 4, 5 units. Same here, 5 units. Okay, so we have two squares. One is more of a diamond on an angle, and this outer square here, which has straight lines. So we know these are 5 units each, so we can figure that out as 25, which you'll actually see on this proof part right here. But I'm just wanted to finish highlighting all these triangles and such. So look, we have these inner triangles as well with a height of 2 and a length of 3. And if you look at them all, they'll be 2, 3, 2, 3, 2, 3 units long. So why don't we look at a proof? So we can, like I said, we can measure the outer square, EFGH, and we can figure out these small squares because we know the area of a triangle. So we just subtract the big triangle from the small one. And here's the work here. I noted each of my triangles just for clarity's sake, and I noted the two squares. And here's our formulas. We know the area of a triangle is half of its base times its height, and the area of a square or a rectangle or any quadrilateral is its base times its height. So here are each of the lines. E, B, F, D, C, G, H, A are 3, and that's the long sides of these triangles. H, C, D, G, B, F, E, A are the short sides. And since they're all congruent, we can just figure out the one calculation once and then multiply it by 4. Here we have that. We only need one triangle 4 times. Here's the calculation. We get 3 for the area of each of the small triangles. Multiply by 4 and we get 12. 12 square units for the total of the 4 red triangles. And let's figure out the big square here. The area of EFGH is its base times its height, which we said earlier was 5 times 5, gives us 25. Okay, not too bad. Now we just need to subtract, and we get 13, which gives us that inner triangle. As we can tell, is the big triangle minus the 4 small triangles gives us that inner square of 13 square units. So what if we wanted to figure out one side? Well, we know all these sides are congruent because we counted them by doing rise over run. A to B is up 2 over 3. Hey, that's just like that triangle. Keep that in mind. And since all 4 sides are that same length by going over 2 down 3 or up 2 over 3, we just take the square root and one side is the square root of 13. I would just leave it as the square root of 13. Don't try and figure that out on your calculator because it's much too long and this is nice and compact. So, why did I say to keep that in mind? Well, let's look at this other way we could solve it. We know these are right triangles, right? What do we know about right triangles? My favorite guy, Pythagoras, has this theorem, a squared plus b squared equals c squared. So let's just figure out the length of a side, c, which is what we wanted as well. And we calculate c to be the square root of 13, so it returns. And then we just square that and get 13 for the area of that inner square. Not too bad, I think. It's a fun way to represent how we actually do the distance formula on a graph. As we know, that is also connected to the Pythagorean theorem. And I figured it would be a nice, fun way to do some math on Halloween. Well, have a nice Halloween.